Hi, I'm Antonio Selle, and in this video we are going to illustrate with the Matlab example how to extract samples of a Gaussian process. In this first video we will just discuss sampling the prior with no actual observations of the Gaussian process value, and we'll discuss the case with observations in a later video. A Gaussian process is a kind of stochastic process, which is the formal way of dealing with what we would call a random function. We will set the interval from -2 to 3, and realizations of that process, well, will be this function, or this one, or this one, and, well, we will have some, let's say, confidence intervals, where 95% of the cases this thing will be in, and some mean value, so that, 50% of the cases we will be above the mean and 50% below the mean. So, formally stating that and obtaining those samples with Matlab is the objective of this video. And the basic of it all is the covariance kernel. My random function, we will assume that it is generated by something so that the covariance between the function at one of the points and the function at a different point is given by a certain function that we will name as the covariance kernel, which depends on x1 and x2. So if x1 coincides with x2, then we will have the variance of the function at the given point, and if x1 and x2 are different points, then the higher the covariance, the higher the statistical relationship between them. Well, we'll see some simulations later on, but the basic idea is that we must define a covariance kernel, and that covariance kernel is defined in this line, and this is the so-called squared exponential kernel that resembles the normal probability density function, but conceptually it has nothing to do with it, because this is a measure of covariance between samples of the process and not of the probability of something. So please do not mix unrelated terms. We can put here whatever function, well, let's verify certain conditions, but okay, we have a lot of freedom in putting here functions that, okay, for instance, in this case, it depends only on the absolute value of the difference between x1 and x2, and in that case, these kind of functions generate what is called an stationary stochastic process, because the behavior is sort of the same everywhere, and the statistical relationship between x1 and x2 only depends on distance and not on actual position in the horizontal axis. Okay, but the idea is that this squared exponential covariance kernel just means that the covariance, the correlation, let's say, between the values of the functions decreases with distance. So when covariance has decreased quite a lot, then roughly the values of the function separated a given large distance are statistically independent. So this is the meaning of the covariance kernel. If we have a lot of points to compute variance or covariance between them, then we need to build a covariance matrix. So in this function capital K, if we have lots of points in x1 and lots of points in x2, we use the covariance kernel to build a matrix with all possible pairs of points in x1 and x2. So this is the core idea. And the next idea is that we will use that K in this function, for predicting the Gaussian process, that, okay, the lines here, we will discuss them in a sequel video when we have some observations. Now we just will return the mean and covariance matrix at a given set of test points x1. The mean will be this quadratic function. I just invented it, you can put whatever function of x you wish, and the covariance matrix between the values of the function at all points x1 is now here a set of samples, will be just, well, evaluating the capital K matrix. So in our particular case, I will set up 201 test points. So this predict GP stuff will return 201 mean values and that 201 times 201 square covariance matrix. And our goal will be generating realizations of the Gaussian process using that information. My process is stationary, and indeed the covariance matrix, it will have variance in the diagonal, and as it's stationary, the variance will be identical for all test points. And then, as the test points are evenly spaced, the covariance between one test point and the next will be 0.3597. Here we have it. This covariance matrix is symmetric. Then if we are separated 2 units, 2 sampling periods, let's say, then covariance is 3589. So this covariance matrix has a band structure, So this is the structure of the covariance matrix. And then my stochastic process, even if, there are infinite samples in it, well, okay, we will discretize and obtain samples at those 201 points. So this will be considered to be a multidimensional random variable, 201 random variables, which have some covariance between them. So we need to sample them. First, if we look just at the diagonal, this is variance. Standard deviation will be the square root of that, which is 0.6. So I can plot the mean and the mean plus and minus twice the standard deviation to get the 95% confidence interval of these random functions. So, well, if I plot that, here we have a quadratic mean function in blue and the lower and upper 95% confidence bounds in red. So if we want samples of these 200 random variables, we can use the multivariate normal random function of Matlab to generate samples of those 201 random variables with some correlation. Actually, inside this function, Matlab computes diagonalization or Cholesky factorizations of the covariance matrix or whatever. It's conceptually important, but not the objective of this video. In here, we will just use that function as a black box. So we give it the mean, 201 points, and the covariance matrix, the square matrix 201 times 201. And then, well, if we add this at the diagonal, well, this is almost zero. It's just negligible, but okay, this number here, this can be considered a measurement noise variance in the sense that, okay, adding something in the diagonal just adds variance at the points, but adds no correlation, covariance with other points. So it's kind of some more noise at a particular point that is uncorrelated with the values of the process at other points. So this is the kind of model we usually implement to model measurement noise. N trials is the number of realizations I wish. And so, for instance, I wish 3 realizations, and then this f1 variable returns me 3 rows of 201 realizations of this multivariate normal distribution, which is the Gaussian process. So we just need now to plot it. All this code is just cosmetic. This line plots that f1 stuff. The rest is, colors, whatever, and well, we will superimpose the mean and confidence intervals to get a glimpse on what we are doing. And then here we have it. We have the 3 realizations, the purple or greenish lines that lie in between these confidence intervals. And well, we can repeat that again and again and again. And well, these are the kind of realizations of this random process. If instead of 3 I wish to draw 500 of them, then here we have 500 realizations, so they concentrate indeed in the band given by the confidence interval, so that, well, 95% confidence interval means that more or less only 5% of the samples, so 25 of the lines, will be outside their red dotted band, and well, every time we have a different stuff, but this is how it works. If we now go back to our 3 trials like this, and we change the correlation distance, if in the covariance kernel my correlation distance instead of 0.65 it's 0.15, it means that the distance at which variables become independent gets divided by more or less 4. So we have like 4 times more randomness in my realizations. So here we have them. Things move up and down 4 times faster with 4 times more frequency. If my spatial correlation distance decreases by a factor of 4, then the bandwidth of my power spectral density increases by a factor of 4. Things go up and down with 4 times more frequency. Then this is more jaggy than before, and of course, if we go to the other extreme and we set a correlation distance of 10, well, then the function will be very smooth. Here we have 3 realizations in which, if the function is below the mean at some point, given the high covariance at high distance, then it will be below the mean until a long distance away. So the increments for the mean will be very low frequency, very low bandwidth. And if we repeat, well, we get this kind of very smooth samples of my Gaussian process with a very large correlation distance. If I add now some measurement noise, then the realizations have the underlying clean, low bandwidth Gaussian process plus white noise uncorrelated with previous or posterior samples. So we'll end here. In this video we have seen how to sample a Gaussian process given a prior covariance kernel, and we have discussed how to integrate measurement noise and the meaning of a correlation distance in the horizontal axis regarding the randomness, the bandwidth of the power spectral density, and how fast things go up and down in the vertical axis. In a forthcoming video, we will incorporate some observations saying that, for instance, I may have measured the velocity of a car in different points of a motorway, and maybe I measured this velocity at this point and this velocity here, so I wish to obtain the most likely interpolation, let's say. So the code will require slight modifications. We'll discuss, as I said, in a sequel video. For the moment being, we end here. Thanks for watching.